Welcome to the third presentation in Unit 10 entitled Drop the Base. It says anger is an acid that can do more harm to the vessel in which it is stored than to on anything on which it is poured. Mark Twain. So what we already know. We already know that acids are in solutions with hydronium ions in solutions. Bases are solutions with hydroxide ions in solutions, and that acids and bases are classified as weak if they do not ionize completely. So, when we go on what we learned in the lab, we learned that indicators can be used to tell when the pH changes. So you start off with a solution that may be red or maybe purple, and as you slowly add base to it, you get to the point where it reaches what we call the titration equivalence point. It actually changes color, so it changes from red to blue. And if you notice, it happened all at once. There was not kind of a gradual change to blue. It was very, very red, and then all of a sudden it changed. So acids and bases react in what's called neutralization reaction, and the titration is a very, very, very useful tool, and it can be used to determine the concentration or the molarity of an unknown. So, the neutralization reaction is where an acid and a base react to form a salt and water. And so you see this. This is the general equation for an acid. It's HA. And this is the general equation for a base, BOH. Once again, we're working with the Arrhenius definition of the acid. So you have HA plus BOH gives you a salt, and the salt is Ba. Okay, where you have B, which is the positive cation, and you have A, which is the negative anion, and water. Okay, so as the neutralization reaction occurs, the pH gets closer and closer to 7 because whatever you initially measured it with, let's say you had an acid to begin with and the pH was 1, as you add base to it, you are destroying the acid. The acid no longer exists. And because of that, you're getting closer and closer to neutral. Now, indicators are used to change the color when the pH changes. Okay, there are several different indicators. There's hundreds of different indicators depending on the range of pH in which you want to use. And so that's the key point, is where do you want it to indicate that there is a change in pH? Some people are interested in the pH change from 1 to 2. Some really want to know when the pH is 7, and that's pretty common because you want to know when it's been neutralized. So whenever you do this, you have to take into account, you have to select your indicator based on what you want to know. So a lot of times the pH can be used to find what's called the equivalence point. The equivalence point is where the number of moles of acid equal the number of moles of base. Assuming that both of them are strong acids, strong bases, and monoprotic, you end up getting a pH of 7 at the equivalence point. So the equivalence point is where the number of moles of acid equal the number of moles of base. So those two things are equal to each other. Generally speaking, the pH is 7 whenever you have monoprotic strong acids and strong bases. This right here is a graph of pH versus the volume that you add. So you end up starting with an acid, and as you add acid, it doesn't change very much to begin with. So you have a very small change in the pH value. But right here, you see a very, very, very large jump in the acid. And that has to do with the fact that, remember, pH is a logarithmic scale. Okay, so as you slowly add the acid, there's not much change at the beginning, and then all of a sudden there's this big jump, and then it levels off again because of the whole idea of it's logarithmic. So like we said, titration is a common tool for quantitative analysis because you can actually calculate how much of an unknown substance there is. A lot of times the unknown substance is called an analyte because it's the substance that you're actually trying to look at. Remember, this right here is a burette. Okay, the burette is used because you can get very, very accurate measurements of volume. Okay, and the indicator is used to change color when a pH reaches a certain point. And so what you're doing is you're comparing a known to an unknown, and you're using what you know to figure out what the unknown is. That's the whole goal. So now, whenever we do these, it's helpful to create what's called a rice chart. Okay, whenever you have a rice chart, the rice chart is generally considered to be reactants, and then you have initial, you have change, and you have equilibrium. So whenever you have the rice chart, reactants, initial concentration, change, and equilibrium. Whenever you use this, it helps keep track of your data, and is really, really, really important when you're talking about equivalence point or neutralization reactions. Okay, you've got to keep track of what you have at which points. So it says how much 0.15 molar sodium hydroxide needs to be added to a solution of 25 mils of 15.8 molar HCl in order to reach a pH of 7. So you should realize that both of these are strong acid, strong base, and it's a titration. Because of that, we can say that the pH is going to be 7 when the number of moles of acid equals the number of moles of base. Now, if you remember, I don't actually have the number of moles of acid or base, but I do have the concentration. So another expression would be the molarity of the acid times the volume of the acid equals the molarity of the base times the volume of the base. So when you plug your numbers in at this point, you get 15.8 times 25, and technically I probably should convert 25 mils into liters, but because I want liters on the other or milliliters on the other side, I'm not going to be able to, or I could just leave it as it is because it's a ratio. So now on the other side I have 0.15 molar of sodium hydroxide, and then I can calculate the volume of the base. When you do this, you would take 15.8 times 25, and you would divide both sides by 0.15. Okay, when you do that, you get the volume of the base to be about 2,633. Because you were in milliliters with your initial value for volume, this value is also in milliliters. So if you were to look, it kind of shows you the power of a concentrated acid versus a diluted acid. So here you have a diluted acid and a concentrated acid. It takes almost 100 or over 100 times the volume to neutralize the concentrated acid. So it says, what is the molarity of KOH? So in this case, I'm looking for the molarity of the base. If 73.2 mils of the solution is added to 25 mils of 1 molar hydrobromic acid to reach a pH of 7. So once again, it's the whole idea that you are trying to look for the equivalence point. So the moles of acid has to equal the moles of base, or the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of the base. Once you do this, you can plug in your numbers. You can say, okay, well, I have 1 molar and I've got 25 mils. And in this case, I don't know the molarity of the base. That's something I'm trying to find. But the volume that I had to add to it was 73.2 mils. And you may be asking yourself, well, that's kind of an interesting number. This data almost assuredly came from a titration. Titration, or burettes, are capable of measuring to this degree of accuracy. So because of that, you would divide both sides by 73.2, and when you do, you end up getting the molarity of the base to be somewhere around 0.34 molarity. Now, you should be able to predict how this would change if instead of this was KOH, what if it was CaOH2? And it would change the molarity of the base as well, because at that point you'd have to take into account the fact that there were 2 hydroxyls produced. So just be aware of that whenever you're doing these. It says speculate on the pH at the equivalence point for a solution for the reaction shown below. And in this case, you have this right here, which is acetic acid. Okay, you have acetic acid, and then you have sodium hydroxide. Well, acetic acid is classified as a weak acid, which means that it does not dissociate completely. So not all these hydrogens right here are free to react with this hydroxyl group. So because of that, you'll have free hydroxyls, and so you would predict the pH to be somewhat greater than 7 because of the fact that you have a strong base mixed with a weak acid. Okay, we also need to talk a little bit more about K. So we're going to review K from Unit 9. We're going to look at Ka. Ka is going to be a more specific version of K. Whenever we talked about KSP, KSP was a more specific version of K. So whenever we look at these, the key thing is that only the aqueous and gas solutions are used. We're not going to use anything other than those. We're not going to use liquids. So whenever we look at this, we have the acid and base dissociation. Now, I'm just going to do it for acid, but basically the same thing occurs for a base, except instead of H, you're going to have OH, and instead of A, you're going to have B+. But other than that, it's going to be the exact same. So we say Ka, and the Ka tells me that it's the acid dissociation constant, and you get this right here. Now, when we did it for KSP, we crossed this out. We canceled it out. We can't do this anymore because this HA value is an aqueous solution. So because of that, it has to be included in the Ka expression or the Kb expression. So whenever you look at this Ka expression in terms of strong acids, they disassociate completely. Because of that, this number is basically 0, and these numbers are as high as they can go, say 1 molar. Because of that, when you were to look at a Ka expression, this number becomes essentially infinity. So Ka values are meaningless when you're talking about a strong acid. So instead of that, we just say they disassociate completely. So you have the initial concentration of the strong acid is equal to the final concentration of the protons. Now, whenever you have weak acid, it's different. Weak acids partially disassociate. So because of that, you need the Ka value to figure out the H plus so that you can calculate the pH. So the initial concentration of the strong acid is equal to the final concentration. That no longer holds true when we're talking about weak acids. So when we use Ka to calculate, Ka values are known and can be determined using a table. So if I were to look up a table, I can figure out what this Ka value is. Okay, now we're going to put the Rice chart to use at this point. We're going to say, okay, the initial value that I had is this molarity, and it didn't have any of these because it hasn't disassociated yet. Whenever this disassociates, for example, whenever one of these falls apart, it's going to produce one of these and one of these. So you're going to have, for every HA that falls apart, you're going to produce an H plus and you're going to produce an A minus. So because of that, I don't know how many of them fall apart. So because of that, I represent it by the minus X value. You have then on the other side, for every X of these that fall apart, you produce X on the other side. And so now you have what's called the equilibrium values. You have H plus as being X, which you don't know. A is X, which you don't know. And then this original value you had that is 0.25 minus X. So this right here is an expression because you know this number and there's only one variable that you don't know. So because of that, we can solve it. Now, there is a trick, and the trick is very, very useful when solving these. If you ever have a Ka value that is 10 to the minus fourth or lower, you can actually take this and you can algebraically make it much, much easier. If it is 10 to the minus fourth or less, this number becomes insignificant in the calculation. Because of that, you can cancel this number out, and now you have a number, the Ka value, is equal to x squared over 0.25. That is a much, much simpler calculation in which you will not have to use the quadratic formula. If you have something that is 10 to the minus second, this is no longer true. You can't cancel that term out. And because of that, you would actually have to multiply both sides, and it ends up being a quadratic formula calculation, which is kind of messy. So you're looking for something 10 to the minus fourth or lower. So it says write a Ka expression for carbonic acid. So you should know that carbonic acid is based on carbonate, which is CO3. It has a charge of -2. So because of that, I can say that the equation that you have for carbonic acid is H2CO3 is going to go to 2H plus, and then you have plus CO3 2 minus. Now I do know that carbonic acid is a weak acid, so when I do this, the Ka expression is going to be important. So I'd write H plus, and then I'd write CO3 2 minus. And on the bottom, I'd have to have H2CO3. Now it is important that you are missing one thing. Remember that these values right here, the exponents, are supposed to be the coefficients. So the coefficients are generally 1, but in this case they're not. So this would have to have a squared value right there. So you do need to be aware of the rules for writing K expressions from Unit 9. It says the acid dissociation constant for acetic acid is 1.58 times 10 to the minus fifth. Okay, what is the pH of the solution of 1.5 molar acetic acid? How does this compare to the pH of hydrochloric acid? So if you were to look at it, we would say, okay, I need to write a Ka expression. A lot of times people will write Ka expressions as just H, A minus, over HA. If you wanted to, instead of writing A, you could write it as acetate, COO, CH3COO, but I like this version a little better because it works for everything. So now what I'm going to do is we say for every one of these that falls apart, we're going to produce an X but we're also going to produce an A, or an acetate ion. So we divide it by 0.15 minus X, because that's our acetic acid concentration right there. Now that right there has to equal our Ka value, which is 1.58 times 10 to the minus fifth. At this point, you like the fact that you have a minus 5 right there, because what that allows you to do is pretend like this is not there. I know that it is there, and I know some people have issues with trying to cross it out, but because it's so small, it's not going to come into play whenever you take into account significant figures. So you can just cross it out. So now you have x squared is equal to 1.58 times 10 to the minus fifth, and then we still have that 0.15 term in the denominator. At this point, you would use algebra to solve. We'd multiply both sides by 0.15, and that would cancel out, and then we'd end up taking the square root. When we do that, we get an x value, which remember is really our concentration of H, is going to be 1.54 times 10 to the minus third, and that is our molarity. Now, in the last one, we have the dissociation constant for purity is 1.8 times 10 to the minus ninth. What is the pH of the solution of 0.15 molar purity? So we're going to use just the general equation again, because we're not familiar with the chemical formula for purity, and we're just going to write it this way. Whenever we do that, we know that that's our Ka expression. So now we can say, all right, well, 1.8 times 10 to the minus ninth, that is equal to x times x divided by 0.15 minus x. I really like the fact that that's lower than minus 4, so because of that I can cross this term out, and I have 1.8 times 10 to the minus ninth is equal to, apply both sides by 0.15, we're running out of room right here, and then I can take the square root of that value. Whenever I take the square root of that value, I end up getting a concentration of hydrogen, or A minus, but we're not interested in that, of 1.64 times 10 to the minus fifth. Now that's not actually the answer for this particular question. The question says, what is the pH? So the last thing that I need to do is I say pH is equal to the negative log of the hydrogen concentration. I take this number, I plug it in, and I get pH is equal to the negative log of 1.64 times 10 to the minus fifth. When you plug that into your calculator, you get a pH of about 4.8. Okay, in conclusion, you have what's called a buffer. A buffer is a interesting thing in that whenever you mix a strong acid with a weak base, you create what's called a buffer system. And this allows you to have a system in which the pH does not change very much. So you create what's called a weak acid with its conjugate base. So when we do this, you have something like, you see here, you see acetic acid and acetate. Whenever you have those two in combination, it creates a buffer system which takes a large amount of pH change, or acid, in order to change the pH. So you have buffers in your body, specifically in your blood. Your blood will allow you to maintain the pH of your blood no matter what you eat or drink or how you breathe, and those things won't affect the pH of your blood because of how efficient the buffer in your blood is. Now you can actually create a buffer in the lab as well, but we're interested in pH in the body. So blood is a buffer, breathing regulates pH, so if you've ever wondered why people who hyperventilate, why is that an issue? Because they're just breathing more. The reason why you hyperventilate is it affects the pH of the blood. You end up getting excess carbonic acid in your blood, and because of that, it can actually cause somebody to pass out. Now, eating can also affect the pH in your body. If you drink nothing but lemon juice or tomato juice, or you eat foods like tomato sauce, those can affect the pH in your stomach and also possibly in your blood if it gets that far. But really what it does is it affects the pH in your stomach, and it causes something called acid reflux. Acid reflux.